In this video, we're going to cover section 1.3, trigonometric functions of any angle. So we're going to start off with the definitions of trigonometric functions of any angle. So I'm going to refer to this diagram here to kind of explain where we're going with this. So in the previous sections, when we were referring to the 6 trigonometric functions of theta, right? So let's say sine theta, cosine theta, tangent theta, we were using the leg lengths when we were forming our ratios, right? So for example, sine of theta is equal to opposite over hypotenuse, right? So we were using the 3 legs of a right triangle to set up these ratios. But the assumption was that theta was an acute angle, or an angle whose terminal ray lives in the first quadrant. But theta can be an angle, any angle in standard position. It doesn't necessarily have to live in the first quadrant. We can have an angle whose terminal ray is in the second quadrant, the third quadrant, the fourth quadrant. So that's where we're going to go in this section now. So we're going to look at any angle that's in standard position. So I like this diagram because this angle theta is living in the first quadrant. So we could see that theta is formed, right, by opening counterclockwise. The initial ray is on the x-axis, right? And then the terminal ray lands in the first quadrant. But it's going through this point P, which is just x comma y, whatever the x value is, whatever that y value happens to be, but let's just call it x comma y. So we can form a right triangle, right? If we were to take where P is, right, and draw a vertical line down, you see how now we have a right triangle. So we form this right triangle, right, that lives in the first quadrant. The base of the triangle is x, because that's how far to the right we went, right, before we went up y units to get to that point x comma y, right, that point P. So this vertical distance is y. So the length of the bottom of the triangle is x, the height of the triangle is y. And imagine that this point lives on a circle, and this is an ugly circle, but imagine this point P lives on a circle with radius r, right? Remember, radius is half the diameter. So this hypotenuse really is the radius, right? That's why we're calling it r. It's the radius of this circle whose vertex, right, is at the origin. So once we look at it this way, where the base is x, the height is y, and the hypotenuse is r, we could still apply the Pythagorean theorem, right? So x squared plus y squared would equal hypotenuse squared, or r squared, right? And if I were to take the square root of both sides, we would get r is equal to the square root of x squared plus y squared. So if we were missing one of these leg lengths in this right triangle, if we were missing x or y or r, we could still use the Pythagorean theorem to figure out what the missing value was. So I'm still looking at this from the same perspective that we were in the previous sections, except now I'm not using opposite, adjacent, hypotenuse. Since we're looking in the coordinate plane, the coordinate system, right, we're going to use x, y, and r. But the ratios are still going to be the same. So look, the sine of theta, so here's theta, right? Sine we know is opposite, right, over hypotenuse. So that would be y over r. And that's this ratio right here that I just circled. Cosine we know is adjacent over hypotenuse. So if we look at theta, the adjacent leg is x and the hypotenuse is r. So it would be x over r. And then tangent of theta we learned is opposite over adjacent. Opposite of theta is y and adjacent is x. So we would have the ratio y over x. And then we would have our reciprocal functions, right? So now instead of, like I said, always thinking in terms of opposite, adjacent, hypotenuse, let's think in terms of x, y, and r. So let's do an example. So we'll put this all together and we'll apply it. So look at example 1. So example 1 says, let point P be equal to 1 comma negative 3. Let that be a point on the terminal side of theta. Find each of the 6 trigonometric functions of theta. So let's sketch our coordinate system, right? The point 1, negative 3 is going to be in the 4th quadrant, right? So remember my quadrants. So we have quadrant 1, quadrant 2, quadrant 3, quadrant 4, right? So if I go over 1 and then down to negative 3, I'm going to have this point right here. So this is a point on the terminal side of theta. So here's theta, this big angle whose terminal right lives in the 4th quadrant. Now we want to find each of the 6 trigonometric functions of theta. So let's think about how we would do that. So in other words, we want to find sine theta, cosine theta, tan theta, and then the reciprocal functions. So this is the point x comma y, right? That 1, negative 3. So we know that x is equal to 1, y is equal to negative 3, but we need r, right? So remember, sine theta, if we think back to these ratios, right, that we came up with on the previous slide. So sine is y over r. Cosine theta is x over r, and tan theta is y over x. We have x, we have y, we need r, and then we could complete these ratios. But remember, we know the relationship between x, y, and r. X squared plus y squared is equal to r squared. And if we want to solve for r, right, we take the square root of x squared plus y squared. So we could figure out r, right? So r is going to be equal to the square root of x squared plus y squared, which is going to be the square root of 1 squared plus negative 3 squared. And that's going to be the square root of 1 plus 9. So that's going to be the square root of 10. So now we know what r is. So r is equal to the square root of 10. And r always has to be positive, right? Because it represents the radius in a circle, which is half the distance. Distance can't be negative. X or y could be negative, right? But r can't be negative. R is always going to be positive. So now we're ready to set up our ratios, right? So the sine of theta is going to be equal to y over r. Y is negative 3, and r is the square root of 10. And let's rationalize the denominator, right? So we're going to multiply by rad 10 over rad 10. And we're going to get negative 3 radical 10 over 10. Now let's look at cosine theta. So cosine theta is going to be x over r, where x is 1 and r is the square root of 10. So we're going to get 1 over the square root of 10. Let's rationalize the denominator. So we're going to multiply the numerator and the denominator by the square root of 10. And we're going to get 1 times radical 10, which is radical 10 over 10 for the cosine of theta. So notice sine of theta is negative, the cosine of theta is positive, and we'll talk about that in a little bit. Now tan theta is going to be y over x. So y is -3, x is 1, so the tangent of theta is going to be equal to -3. Now we're ready to get our reciprocal functions. So the reciprocal functions are going to be cosecant theta, secant theta, and cotangent theta. So we're just going to take the reciprocal. So the reciprocal of sine in this case is going to be negative, and let me use red just so it stands out as our solution. So the cosecant of theta is going to be the reciprocal of sine, which is going to be negative square root of 10 over 3. Secant theta is going to be the reciprocal of cosine theta. So reciprocal of 1 over radical 10 is going to be radical 10. And then cotangent theta, the reciprocal of -3 is going to be -1 over 3, or -1/3. So those are each of the 6 trigonometric functions of theta, whose terminal ray lives in the 4th quadrant and goes through the point 1, -3. So let's do another one for practice. Make this a little bigger. All right. So now we have the point -4, 3, and that's on the terminal side of theta. We want to find each of the 6 trigonometric functions of theta. So let's make a sketch. Here's x, here's y. The point -4, 3. So let's say here is -4. Let's say this is +3. So here's my point P. It lives in the 2nd quadrant. So the terminal ray goes through and we form theta, right? So here's theta. And we want to find the 6 trigonometric functions of theta. And we know x is equal to -4, y is equal to 3, right? Because imagine again, we didn't do it in the previous one, but imagine we form that right triangle. You see what I'm doing in red? I'm forming this right triangle. You see how the terminal ray forms a right triangle in the 2nd quadrant, whose base is x, whose height is y, and it'll have a radius of r. We just need to figure out what it is. So let's figure out the radius, because again, we're going to need that in order to set up our ratios. So r is equal to the square root of x squared plus y squared. So it's going to be the square root of -4 squared plus 3 squared, which is going to be the square root of 16 plus 9, which is 25. And the square root of 25 is 5. So r is equal to 5. So now let's set up our ratios. So we want sine theta, cosine theta, tangent theta, cosecant theta, secant theta, and cotangent theta, right? Those are our 6 trigonometric functions of theta. So sine theta is y over r, which is going to be 3 over 5, right? Y is 3, r is 5, so it's going to be 3/5. Cosine theta is equal to x over r. X is -4, r is 5, so that's going to be -4/5. And tangent theta is equal to y over x. And y is 3 and x is -4. So tan theta is going to be -3/4. I'm pulling the negative out in front. Instead of writing it as 3 over -4, I'm just writing it as -3/4. Same thing. And now we're ready for reciprocal functions, right? Cosecant theta is the reciprocal of sine theta. So the reciprocal of 3/5 is going to be 5/3. Secant theta is the reciprocal of cosine theta. So the reciprocal of -4/5 is going to be -5/4. And then cotangent theta is the reciprocal of tan theta. Tan theta is -3/4, so the reciprocal is going to be -4/3. And that concludes example 2. So now let's talk about the signs of the trigonometric functions. And I'm going to go back, and I started telling you in example 1 to start thinking about this. Like I pointed out, well, you see how sine is negative, but cosine's positive, and the angle, the terminal ray is living in the 4th quadrant. So think about a point, if we go back to these definitions of these ratios on this first slide. So actually, I'll do it right here. So here's quadrant 1, quadrant 2, quadrant 3, quadrant 4. Every point that lives in the first quadrant, so x comma y, x is positive and y is positive, right? If the point's in the first quadrant, r is always positive. So no matter what ratio I set up, whether it's sine, cosine, tangent, or the reciprocal functions, every ratio is going to be positive if x, y, and r are all positive, right? So all our ratios are positive in the first quadrant. But if I have a point that lives in the second quadrant, right? So if I go over to the left and up, I'll be in the second quadrant, but x is negative, right? So x is negative and y is positive. So any ratio that involves x is going to be negative. The only trig function that's going to be positive in the second quadrant is going to be sine and cosecant, right? Because that's y over r over y, and both y and r are positive. So only sine theta and cosecant theta are going to be positive in the second quadrant for that reason. Now imagine a point that lives in the third quadrant. X and Y are both going to be negative, right? Because we're going back and then down to get into the third quadrant. So we're going left and then downward. So X is negative, Y is negative. So both sine and cosine theta involve r, but one involves y, one involves x. So r is going to be positive, but y and x will be negative. So sine and cosine and their reciprocal functions are going to be negative if the angle has a terminal ray in the third quadrant when we go to set up those ratios. The only function that's going to be positive is tangent and cotangent, because we're going to compare y over x or x over y, and both y and x are negative. When you compare a negative over a negative or divide negative over a negative, it's a positive. So tan theta and cotangent theta are both going to be positive in the third quadrant. And then if we were to sketch a point in the fourth quadrant, we go to the right. So x is positive, but then we move down. So y is negative. Therefore, any ratio that contains just y and r, or y and x, right? Because a positive and a negative, when we compare them, is going to be negative. So sine theta and tan theta are going to be negative in that fourth quadrant, but x over r is going to be positive, right? Because x is positive, r is positive. So cosine theta and secant theta are going to be positive in the fourth quadrant. So that's what this slide is explaining here. In quadrant 1, all functions are positive. In quadrant 2, just sine and cosecant are positive. In quadrant 3, tangent and cotangent are positive. And in quadrant 4, cosine and secant are positive. Every other function's negative. And this is exactly what I just illustrated using the rationale above, based on what quadrant we're in and if X or Y is positive or negative in that quadrant. So let's look at a couple of examples. Look at example 3. If sine theta is less than 0, meaning negative, and cosine theta is less than 0, meaning negative, name the quadrant in which the angle theta would lie. Well, where is sine negative? Sine is positive in the first and the second quadrant, so sine has to be negative in the third and the fourth quadrant, right? Now let's think about, where's cosine theta negative? Well, cosine is positive in the first and the fourth, so it's going to be negative in the second and the third. And now look, where do we have 2 check marks? In the third quadrant, because that's where sine is negative and cosine's negative. So the quadrant in which angle theta would lie would be quadrant 3. Let's look at the next example. If tan theta is less than 0, or in other words, negative, and cosine theta is greater than 0, meaning positive, name the quadrant in which the angle theta lies. So let's do the same procedure here. So if tangent's negative, let's check the quadrants where tangent could be negative. Well, tangent is positive in the first and the third, right? So that means that tangent's negative in the second and the fourth. Now, where is cosine theta positive? Well, everybody's positive in the first quadrant, and cosine's also positive in the fourth quadrant. Therefore, quadrant 4 is going to be my answer, right? Because that's where tan's going to be negative, but cosine would be positive. And we'll do one more. So look at example 5. If sine theta is positive, greater than 0, and secant theta is less than 0, or in other words, negative, name the quadrant in which the angle theta lies. So where is sine positive? So sine is positive in the first. Hold on, my pen does not want to work right now. Hold on a sec. I don't know why my pen just stopped working. Hold on, this is annoying. All right, we'll see if it catches up. I feel like there's a lag, and that's what the problem is right now. Okay, so we said sine is positive in the first and the second quadrant, and secant is negative. So remember, secant is the reciprocal of cosine. and cosine is positive in the fourth and the first. So that means secant's going to be negative in the second and the third. And this is so annoying that this pen's not working because it's hard for you to follow if I can't draw. All right, you know what we'll do? Let me pause the recording for a second. Okay, I think the pen is back. So let's try this one more time. So sine is positive in the first and the second quadrant, and secant theta is negative, we said, in the second and the third quadrant, right? Because that's the reciprocal of cosine, and cosine is negative in the second and the third. So we're gonna live in the second quadrant, right? Theta would lie in the second quadrant if sine was positive and secant was negative. So this is going to be important, this concept, to help us solve these next couple of questions. So let's evaluate, the instructions are for evaluating trigonometric functions. So in example 6, let's suppose tan theta is equal to negative 1/3. And we know that cosine theta is less than 0, right? Meaning negative. Find sine theta and secant theta. I'm not even going to worry about finding anything yet. Let me just figure out what quadrant theta lives in, right? Because that's going to make my life much easier if we could figure out, all right, what quadrant are we in? So if tangent is negative, right? You see how tan theta is equal to negative 1/3, and cosine theta is negative. Let's figure out what quadrant that is. And if you want to remember it this way, you might have things that you remember from other teachers in the past, but a lot of times we remember all, so all, and then sine is positive in the second quadrant. So we say all students, remember S for sine, and then tangent's positive in the third quadrant. So we say take T for tangent, and then cosine is positive in the fourth quadrant. So just a little way to remember, what's positive in which quadrant is all students take calculus. So we have the all and then the S for sine, T for tangent, C for cosine. So if that's helpful, you can remember it that way. So tangent is negative. So remember, all students take calculus. Tangent's going to be negative in the second and the fourth quadrant, and cosine is negative in the second and the third. So we're in quadrant 2 right now. So suppose I have this angle theta that lives in the second quadrant. Tangent's equal to negative 1/3 and cosine's negative. We want to find the sine of theta and the secant of theta. Now remember, sine of theta is equal to y over r. And secant theta is equal to the reciprocal of cosine theta. Cosine theta is x over r. So secant theta is going to be r over x. So in order to solve this, we need x, y, and r. Now we know tangent of theta is equal to negative 1/3. And tan theta is equal to y over x. But we're in the second quadrant because it's negative 1/3. So is the 1 the negative 1 or the 3 the negative 1, right? Is it y or x? So we have to think about this. Well, if we're in the second quadrant, that means that x is negative and y is positive. So that means that tan theta is equal to positive 1 over negative 3. So the 3 is what's negative, because I had to go to the left and then up, right, for some point P that lives on this terminal ray. So y is equal to 1, x is equal to -3. And now we just need to solve for r, right? And remember, r is equal to the square root of x squared plus y squared. So we're going to have the square root of -3 squared plus 1 squared, which is 9 plus 1, and we're going to get the square root of 10. So r is equal to the square root of 10. And now I could figure out my ratios, right? So sine theta is equal to y over r. So y is equal to 1, and r is equal to the square root of 10. And if we rationalize the denominator by multiplying by the square root of 10 over the square root of 10, we're going to get radical 10 over 10. And it's positive, and it makes sense because our theta's terminal ray, right, the angle's terminal ray lives in the second quadrant, and sine is positive in the second quadrant. Now, secant, which is the reciprocal of cosine, should be negative, right, because we're in the second quadrant. So let's see, if we take r, which is the square root of 10, and put it over x, which is -3, right, we get negative radical 10 over 3 for the secant of theta, and it's negative, which is what we expected. So let's look at the next one, very similar. So example 7. So given cosine theta is equal to 4/5, which is positive, so cosine is positive, right? And theta is in quadrant 4. So we're being told that our angle lives in quadrant 4. Find the remaining trigonometric functions of theta. So we're given cosine, so now we want everything else, the other 5 trig functions of theta. So let's sketch our angle, right? It's theta lives in quadrant 4. So let's say that that's theta. Now in quadrant 4, x is positive, y is negative. And cosine theta is equal to x over r. Which in this case we're being told is 4 over 5, right? It was given. So we know that x is 4, r is 5. But in order to get the remaining trig functions of theta, we need y, right? So let's solve for y. So remember, x squared plus y squared equals r squared. So we're going to get 4 squared plus y squared equals 5 squared. And if we solve for y, we're going to get y squared equals 5 squared minus 4 squared. So y squared is equal to 25 minus 16, right? 5 squared minus 4 squared, which is 9. Take the square root of both sides. And the square root of 9 is positive or -3, right? But you have to remember, what quadrant are we in? Like we said before, we're in the 4th quadrant. And what's true about my y values when we're in the 4th quadrant? They're negative, right? So my answer is -3. Y is equal to -3. So now I'm ready to set up my ratios. So we want sine theta. We already have cosine theta. We want tangent theta. Let's get the reciprocal functions. So we need cosecant theta, secant theta, and cotangent theta, which I'll put over here. So sine theta is y over r. So y is -3, r is 5, so -3/5. Tan theta is y over x, so we're going to have -3 over 4. Cosecant theta is a reciprocal of sine, so reciprocal of -3/5 is -5/3. Secant theta is a reciprocal of cosine. Cosine's 4/5, so this is going to be equal to 5/4. And then cotangent theta is going to be the reciprocal of tan theta. The reciprocal of -3/4 is going to be -4/3. And those are the remaining trig functions of theta. So next we have reference angles. So the definition of a reference angle is that it's the positive acute angle that's formed with the terminal side of theta and the x-axis. So for example, and we're going to need reference angles when we start solving trigonometric equations. So in order to do that, we need to get comfortable with reference angles. So we're letting theta be a non-acute angle, meaning it doesn't live in the first quadrant, because all angles that have a terminal side in the first quadrant, they're acute because they're between 0 and 90 degrees. So assuming the angle is either lives in the second, third, or fourth quadrant, it forms a reference angle, and it's formed by the terminal ray or the terminal side of the angle and the x-axis. So for example, look at this first diagram. If I have an angle that lives in the second quadrant, so we call it theta with a little prime just to differentiate it from regular theta. So we have theta, right? But this angle that's formed, and I'll use green because that stands out. This angle that's formed with the terminal ray and the x-axis, that's theta prime, which is the reference angle. So for example, if I have an angle that lives in the third quadrant, right? So theta, the terminal ray is in the third quadrant, the angle that's formed with the terminal ray and the horizontal axis, the x-axis, that's my reference angle. And if we have an angle whose terminal ray is in the fourth quadrant, the reference angle would be this one in green. That's made again with the horizontal axis and the terminal ray. So the reference angle is formed using the terminal side of theta and the x-axis. You would never use the y-axis. That's not the definition of a reference angle. So now how do we find the reference angle? Well, if we're in the second quadrant, because we know if we go halfway, that's 180 degrees, right? So to get the difference, right, of theta and 180 degrees, which would be the reference angle, we take 180 degrees and we minus theta, and that would leave us with the reference angle. And I have them down here also. So if our reference angle is in the third quadrant, now theta is bigger than 180 degrees, right? We went more than 180 degrees. So we would get our reference angle theta prime by taking theta and subtracting 180 degrees. And if my reference angle is in the fourth quadrant, to get theta prime, which is my reference angle, we take 360 degrees and we subtract theta. So look, let's practice. So example 8, find the reference angle theta prime for each of the following angles. So let's say theta is equal to 210 degrees. A 210-degree angle lives in the third quadrant. So this would be theta equals 210 degrees. The reference angle is what's formed with the terminal ray and the horizontal axis, this angle that I'm drawing in green here. So since we're in the second quadrant, we take 210, so take theta and subtract 180 degrees. And my reference angle is going to be 30 degrees. So that's the angle that's formed with the terminal ray and the horizontal axis. That's this guy right here. So the reference angle for theta, which is 210 degrees, would be 30 degrees. So let's look at the next one. Let's look at B, which is 300 degrees. Notice I'm only using the 180-degree angle or the 360-degree angle because the reference angle is made with the terminal ray and the x-axis. Like I said before, never the y-axis. So let's sketch an angle of 300 degrees. So that's going to live in the fourth quadrant. So let's say that this is theta is equal to 300 degrees. The reference angle is the angle that's formed with the terminal ray and the x-axis. So this angle in green. So we get that when we're in the fourth quadrant by taking 360 degrees and minusing theta. So we're going to subtract 300 degrees and we get 60 degrees for our reference angle, which is this angle right there. So let's look at the next one now. Let's look at C. So for C, I have an angle of 135 degrees. So that angle is going to live between 90 and 180 degrees, right? So let's say this is theta. We want the reference angle theta prime, which is formed with the terminal ray and the x-axis. So if we're in the second quadrant, we take 180 degrees and we subtract theta, which is 135 degrees. And we're going to get 45 degrees for our reference angle. It works the same way if we're in radian measure. So look at D. We're just going to be in radian mode, right? So we have pi radians and 2 pi radians, right? So if theta is equal to 7 pi over 4, that angle lives in the fourth quadrant. So theta is equal to 7 pi over 4. And we want to find the reference angle. So the angle that's made with the terminal right and the horizontal axis. Now, if we were in degrees, we would be looking at this scenario, right, that I just circled because we're in the fourth quadrant. So we would take 360 degrees minus theta, but we're not in degree mode, we're in radian mode. But 360 degrees is equivalent to 2 pi radians, right? So we would just do 2 pi minus 7 pi over 4 radians. So it's the same calculation, it's just that we're in radian measure. So we're going to take 2 pi minus 7 pi over 4. We need a common denominator, right? So we could write this as 8 pi over 4, right? Because 8 divided by 4 is 2, so that's the same thing as 2 pi, minus 7 pi over 4. And 8 pi minus 7 pi is going to be 1 pi. So 1 pi over 4 is equal to my reference angle. So let's look at E. So E, theta is equal to negative 240 degrees. So my angle is going to live in the second quadrant, but it's negative 240 degrees, right? So we had to go past negative 180, and it's going to be between negative 180 and negative 270. So my reference angle, like I keep stressing, is always formed with the terminal ray and the horizontal axis. So it's going to be this angle that's formed in green. So this would be my reference angle, theta prime. So now we need to figure out what the measure of that angle is, right? What is that angle that's being formed with the terminal ray and the horizontal axis? And if we're in the second quadrant, right, which is this case, theta prime, our reference angle, is equal to 180 degrees, but in this case, it's where we went in the clockwise direction, so it's negative 180 degrees, and then minus theta, where theta is negative 240 degrees. And negative 180 degrees minus negative 240 is going to be positive 60 degrees. Reference angles are always positive. It's the positive acute angle that's formed with the terminal ray and the horizontal axis. And let's do one more. We're back to radian measure. So for part F, you see how theta is equal to 3.6. There's no degree sign there, right? So it's radian measure. So remember, pi is approximately 3.14 radians. And then 3 pi over 2 is about 4.71 radians. 3.6 is between 3.14 and 4.71. So our angle lives in the third quadrant. So here's theta is equal to 3.6 radians. And we want to find the reference angle that's formed with the terminal ray and the x-axis. So this angle in green. And remember, if we're in the third quadrant, we take theta and we minus 180 degrees if we were in degrees, or in this case, we're going to take theta, which is 3.6 radians, and we're going to subtract 3.14, right? 180 degrees is equivalent to pi radians or 3.14 radians. So my reference angle is going to be equal to 3.6 minus 3.14, which is 0.46 radians. And that would be my reference angle. So in the next example, you're going to see how reference angles are going to be useful to us. So example 8 was really just practicing how to determine what our reference angle is. So let's look at this last example. So example 9 is the last example. So before we do that, so why would we use reference angles? They're helpful in evaluating trigonometric functions. So the values of the trigonometric functions of a given angle theta are the same as the values of the trigonometric functions of its reference angle, theta prime, except possibly for the sine, because remember, depending on what quadrant we're in, sine, for example, might be positive or it might be negative. Same with the rest of your trigonometric function values, right? Depends what quadrant the angle lives in. A function value of the acute reference angle, theta prime, is always positive. So remember, reference angle is always positive. However, the same function value for theta may be positive or negative. Again, it depends on what quadrant we live in. So the value of a trigonometric function of any angle theta is found the following way. So the first thing we're going to do is find the reference angle, and then that particular function value for the reference angle. And then we have to determine, the quadrant in which theta lies in order to get the appropriate sign. So look, this is what we're doing. So example 9, use reference angles to find the exact values of the following. So the sine of 300 degrees. And I just want to point out, so remember, back in the previous section, section 1.2, remember we went over this table of trigonometric function values for sine, cosine, and tangent for 30, 45, and 60 degrees, those special angles, and we used those special triangles. So let's keep this in mind, the 30, the 45, the 60-degree angles, and these exact trigonometric function values. So let's go back to the worksheet. Let's use reference angles to find the exact value of the sine of 300 degrees. Well, I'm not picking up the calculator. That's not the point here. So what I want to do is I want you to see something. Look, the sine of 300 degrees. Well, 300 degrees has a terminal ray that lives in the fourth quadrant, right? It's between 270 and 360. I want to know what the sine of 300 degrees is. Well, let's look at its reference angle. The reference angle for an angle of 300 degrees is this green angle right here, right? And the way we get that is by taking 360 degrees minus theta, which is 300. And we're going to get 60 degrees. So my reference angle is 60 degrees. So the fact that the reference angle and the angle of 300 degrees, they share the same terminal ray. So they're going to have the same trigonometric function values. It's just the trigonometric function values of all of our reference angles, since our reference angles are positive acute angles, they're all positive. But we have to think about, okay, sine, the sine of 300, but we're in the fourth quadrant. Is sine positive or negative in the fourth quadrant? And let's remember, all students take calculus, right? We're in the fourth quadrant. The only thing that's positive in the fourth quadrant is cosine, and it's reciprocal. Sine is negative in the fourth quadrant. So we could say that sine is equal to a negative value, right? The sine of 300, but it's going to have the same function value as an angle of 60 degrees. So let's go over to our table. Let's look up the sine. So here's sine. Here's 60 degrees, and it's radical 3/2. So the sine of a 60-degree angle is radical 3/2. So then the sine of a 300-degree angle is going to be negative radical 3/2, since the angle lives in the fourth quadrant, but it's still going to have the same ratio as an angle of 60 degrees because they share the same terminal ray. So let's do another example, the cosine of 150 degrees. So 150-degree angle lives in the second quadrant. It's less than 180, right? But bigger than 90. So let's say this is theta is equal to 150 degrees. Let's use the reference angle to help us get that answer. So to get the reference angle, if we're in the second quadrant, we take 180 degrees and we subtract theta, which is 150. So my reference angle is going to be 30 degrees. So we can use the reference angle of 30 degrees to get the cosine of 150 degrees. We just have to think about the sign, right? Is it positive or negative? Well, in the second quadrant, cosine's negative, right? Because sine and cosecant are positive. So cosine's going to be negative because we're living in the second quadrant, and it's going to have the same function value as our reference angle of 30 degrees. So let's go back to our table, and now let's look up cosine of 30 degrees, and that's going to be radical 3/2. So the cosine of 150 degrees is going to be negative radical 3/2. Let's look at C. So the tangent of 225 degrees. So 225 degrees is bigger than 180 degrees, but less than 270, right? So it's going to live in the third quadrant. Find your reference angle, which is this angle formed with the horizontal axis and the terminal ray. So remember, when we're in the third quadrant, we take theta, which is 225, and subtract 180. And theta prime, my reference angle, is going to be equal to 45 degrees. So the tangent of 225 degrees is going to have the same function value as the tangent of 45 degrees, with maybe the exception of the sine. So we have to think about what quadrant we're in. So we're in the third quadrant, but tangent's positive in the third quadrant. So tangent of 225 degrees is going to be positive, and it's going to have the same function value as an angle of 45 degrees. So let's go to our table and look up tangent of 45 degrees, and that's going to be 1. So the tangent of 225 degrees is equal to 1. And let's do one more. So the sine of 300. So let's sketch an angle of 300 degrees. So an angle of 300 degrees lives in the fourth quadrant, less than 360, but more than 270. So let's say this is theta is equal to 300. And as I'm doing this, I'm realizing that we just did this one in A. I don't know why there's a repeat of that. Let's change it to cosine. So instead of sine of 300, let's make this cosine of 300. So our angle lives in the fourth quadrant, theta equals 300 degrees. Let's find our reference angle. My reference angle is this angle in green, and it's going to be equal to 360 degrees minus theta, which is 300, and 360 minus 300 is 60 degrees. So that's my reference angle. So the cosine of 300 degrees is going to have the same absolute value of the cosine of 60 degrees, but we just have to look at the sign, right? So we're in the fourth quadrant. So now we're in the fourth quadrant, and cosine is positive in the fourth quadrant. So cosine is going to be positive, and it's going to have the same function value as the cosine of 60 degrees. So let's go to our table of values, and we're looking at cosine of 60 degrees, and that's 1/2. So the cosine of 300 degrees is equal to positive 1/2. So this wraps up section 1.3. In the next lecture, we're going to cover section 1.4.